this is a bit old data, sorry. Our location is here, our location here, in the central region in Japan, and close to Nagoya. Also Toyota, headquarter office of Toyota Motor Company. And around 250 kilometer west side from Tokyo, and east side from Osaka. So actually very convenient region, right? Because we have a Shinkansen system, bullet train system, so easy to move to both sides. Also Kyoto and Hiroshima. Fukuoka a bit far, right? And well, we are actually a very small university. Total number of students, including graduate students, is only around 2,000, right? But we have recently, this is a bit reduced, but around 10% international students. I think currently Indonesian is highest. Sorry, this is a bit older data, but Malaysian, Vietnam's major students as well as Indonesian. And the number of academic staff is more than 10% of students. So if you have some interest in our university, feel free to ask me. And also you can drop by when you have a chance to come to Japan. And we have some international collaborative education program. Yeah, I'm in charge of double degree program for graduate school, master's program with University of Stuttgart. And also this program is now, I think, double degree program with Bandung Institute of Technology, Indonesia. And also we have some program with Hasanuddin University in Indonesia. And regarding my activities, as I mentioned, we established this collaborative laboratory with University of Stuttgart. This is me, and this is Professor Sawadoni in Stuttgart. And we actually, our group established double master degree program with Stuttgart. Now, this is Stuttgart homepage, and they said Toyohashi University Technology is one of the best universities in Japan, right? Right. So if you are interested in joining this kind of program, yeah, international students can join this program. You can experience kind of the major university in Europe as well. And also, we established UITM TUT collaboration lab last year. UITM is a university technology matter whose number of students 160,000. I think it's biggest university in Asia, right? So this is a photo in the opening ceremony. We have this kind of collaborative laboratory, UITM TUT laboratory. So this is me. Okay, and our university is the main focus, main role is to accept Kosen students from the third year. I'm not sure you know the Kosen system in Japan. After junior high, Kosen system provides 5-year program in technology, right? So regular students are from high school to the first year. High school has 3 years after junior high. This is 5 years after junior high. And we accept only 80 students in the first year, around 80, sometimes 100, right? Around this number of students. Well, and from third year, we have 300 60, right? 60 students. Right? So total will be 440. So major students of our university are graduates of Kosen students. So this is a unique, feature of our university. So they are very practical, right? Practical subject-oriented students. And most students are going to master course, right? 395 out of 440. And spend mostly 2 years. And PhD program are very small, right? Less than 10% of master students. Most students are going to Japanese industries. So this is a unique structure of TUT. Other university basically accept students only from high school. Right? Of course, some are transferred from other universities, and some Kosen students are going to normal universities, but most target high school students in other universities. So we are very unique. I think you are interested in the rank of our university, Times Higher Education rank. Probably you want to know the level of our university, right? This is includes only Japanese universities. Actually, University of Tokyo is the best university in Japan. But in this, this also, bit older data, Tokyo University is the best. And Osaka, Tokyo Tech, Kyoto University. I think Kyoto University is, probably know this name. Second university in Japan, I think. So we are around here, right? 36. Most national universities are around this level in Japan. Excuse me. International students ratio, this column is a bit higher than other universities, right? Number of students are smaller than other universities. But there's one more unique feature of our university. This is this is in Japanese. University Fact Book, year 2022. This graph shows the research fund from university per academic staff, not governmental fund, fund from industry. Because we are a very small university, total amount is big, right? And so divided by number of academic staff. So comparison will be fair, right? So this shows we are the highest, right? Higher than Tokyo Tech, Tokyo University, Osaka University, right? This year, right? This year, year 2022. This year, maybe, I think around this level, but 2022, we are the highest. So this is one unique feature of our university. Because our students are very practical, right? Had a practical education. So they are highly evaluated in industries. So this is one of the reasons that we are the highest this year. Interesting feature. So this is the end of my introduction of our university. If you have any questions, please feel free to ask me anytime. Okay. If no questions, I'd like to go into systems engineering, which includes optimization and dynamic control. So our laboratory name is Systems Engineering Laboratory. Okay. Systems engineering I think, our students say, topic is unclear. Right. Because system engineering is included in not only mechanical engineering, so we can consider electrical system, economic system, including, city system or, kind of information system also. So system engineering is actually an interdisciplinary subject. Some consider, so this is rootless, right? Topic is unclear. But our fundamental is, for example, mathematical modeling, including dynamic modeling. And after modeling, we can optimize the system, right, by using this model. And we can make a control strategy of the system by using this model. So, this is our basics, right? So today, I'd like to explain basically optimization and some dynamic modeling, right? And control, of course. This system engineering covers this kind of area. And we apply this subject to industry-related problems. Mostly because I am with the mechanical engineering department, mostly mechanical control subject. Okay. I think the among this optimization is most important. Because mathematical modeling is considered. The objective is modeling is for optimizing existing system, right? And the control objective is the for optimizing the performance. So optimization is most important in system engineering, in my view. So I'd like to briefly explain the optimization, concept of optimization. I think some of you studied this concept in lectures already. This is a very typical topic in optimization, traveling salesman problem. Salesman are asked to visit all customers. This is a office. Start point is office. And if the salesman takes closest order, first, closest point here to the office, he visits here. And the next closest point here. So next here. The next one here. Then he will take this route. So this is not optimal from the viewpoint of total distance, longer than this case. This is optimal trajectory, optimal path. So this is called traveling salesman problem. The objective is look for minimum, not only distance, minimum cost. Strategy. Right? Sometimes pass, sometimes this kind of pass, sometimes the time to be taken considered as cost, or some budget costs are taken for the evaluation criterion. Right? You understand? So this is optimal, typical problem in optimization. Looking for best strategy for doing something. So we next closely look to this problem. So in optimization problem, we have to define objective function, right? Which to be minimized or maximized. Or for example, to maximize the profit, right? In this case, because this is a traveling salesman problem, minimize total distance, right? And in optimization problem, we have to define variables, right, to be changed, which we can change, right? This is visiting order, just visiting order, right? And also we have to define constraints. In this case, visit all customers. You cannot skip some customers, even if you dislike him or her. You have to visit him or her, right? This is constraints. And you have to return to the office at last, finally. You cannot directly go home. Right? First, finally, once you have to return to the office and report, I visited all the customers, something like that. Okay, this is a structure of optimization. So once this problem is mathematically or logically formulated, nowadays many solvers are available, sometimes in the internet. Python provides many solvers. So we just look for suitable solvers nowadays. We don't have to write optimization program from the scratch, right? We can borrow the such kind of the existing tools, right, for solving our problem. This is a strategy of our laboratory, right? Company asks us to solve some problem, right? Industrial problem, and we in our laboratory we formalize and formulate this kind of problem. Right? We'll ask them what you want to minimize or maximize, right? What can be changed, right? Budget cannot be changed normally. Right? Just are you able to change hardware or only software can be changed? They are kind of variables, and also we have to define constraints, right? Motion time should be less than this time, or obstacle must be avoided, something like that. Okay, if no questions, I'd like to, I'd like to go into our examples of optimization application to actual industry-related works in Japan. Right? Optimization, you understand that optimization has wide applications, and also dynamic control has wide applications in industry, right? So if no questions, I'm going to next topic. The first topic is industrial robot control. This one. So this is published in this paper more than 10 years ago. You see the video, right? This is objective to move semiconductor wafer from this position to this position for processing, right? This is typical structure of industrial robot. Because semiconductor is the very precise electrical system, so this must move in the dust-proof environment. dust-proof clean room environment, right? Yeah, or in medical applications, sometimes this is needed. Right? So if you move the robot, there are three actuators, motors, and here's a carried object, right? If you move this robot inappropriately, the robot hits the wall, right? And this is dust proof, right? There are walls to avoid dust. And the robot take take this object from here, move here, and next move to here for some processing. And next move here for some processing. This is a task of a semiconductor warehouse robot. So key point is this, environment is rectangular area. And it has three joints, three arms. And collision avoidance with walls is required. Okay. This is a company request. To generate optimal path from here to here, or here to here, there are many combination are considered of motion. So the topic they request time optimal motion trajectory generation for this robot, right? The robot system is very competitive in this field. Right? They want to reduce the motion time in order to increase the productivity. Right? If the motion is slower than competitors, your robot is not accepted. Right? Other robots, they buy other companies' robot. So very competitive. And also, because this motion is very rapid, vibration occurs sometimes, right? Because this part has, you see, lightweight material, right? So vibration occurs. So we have to generate this kind of vibration considering trajectory. Not only time optimal, but also vibration must be considered, as well as collision avoidance. Normally, this kind requires large computational resources in optimization, right? So we propose, first we propose simple dynamic model. This is a kind of dynamic control problem. Right? And for obstacle avoidance, from this figure, if all joints are in this rectangular area, X and Y values are between Y minimum to X minimum, Y minimum to Y maximum, and for X are between from X minimum, X maximum, then collision can be avoided with the walls. So this constraint is very simple, right? All the joints must be within this rectangular area, right? So this is a simple constraint. And for considering the vibration, actually we measure vibration property by installing this accelerometer here at the end effector, at the gripper, kind of gripper, right? This is a kind of vacuum gripper. You see these folds, right? But this gripper keeps the position of the semiconductor wafer by applying some vacuum force, right? And we measure the vibration property of this end effector. And this is a natural frequency. Sorry, this is in Japanese. And here acceleration. So y-axis vibration are significant this direction. And g-axis and x-axis vibration are much smaller than y. So we consider this dynamic model. This is just a simple mass spring model. Probably you studied in the physics something, right? Vibration. So inertia over this end effector inertia over spring constant will be a square of angular natural frequency, right? So this motor angle and effector angle difference will be a vibration. Right? This is assigned motor angle, right? Commanded motor angle, and end effector position will be different by vibration. So this difference will be vibration. So we, formalize this problem using this simple model. And we consider Newton's equation. This is, sorry, bit skipped, right? And consider this inertia and motor inertia and the spring constant. And this angle minus this angle, motor angle, last motor will be vibration. Right? And furthermore, we have to consider motor torque limitation. Right? Each motor has a power limitation, of course, right? They use these motor powers as much as possible, right? To reduce the motion time. So this is their request. And they give initial states of the robot from here, for example, from here to here, final states. And as I mentioned, all joint must be within rectangular area during motion. And here's a mathematical formulation of trajectory. This is time, right? This is a joint angle, one joint angle, a theta here. And we divide them into endpoints, right? In order to, write optimization program, we have to discretize. We have to consider discrete problem. Not continuous problem is normally cannot be dealt within the computer program. We divide them into endpoints, for example, endpoints, right? And so this delta t is a kind of sampling period. Now this is the objective function. If we minimize delta t, because n is fixed, total motion time is reduced, right? So our one objective is to minimize sampling period. Okay, this one. And as I mentioned, vibration and motion time has a trade-off. Right? In order to reduce vibration, we have to consider vibration term in the also in the objective function. Theta 3 minus theta a vibration. So we consider square of vibration and summation for each point. Each point we can calculate vibration, right? By model, by dynamic model. Yeah, this is dynamic model. Right? But using a dynamic model, we can calculate vibration in simulation. And because this unit and this unit are different, so we apply alpha to consider both. evenly or fairly, right? Yeah, if this unit is very small, right, than this one, this comparison is unfair, right? So we apply weight here. Then, right, as I mentioned, if we minimize this one, total motion time and delta t is minimized, and this is for vibration. And variables, right? This is objective function, as I mentioned in the beginning of my talk today. And the variables are motor angle and motor torque and this delta t are variables in this problem, in this optimization problem. Okay, constraints they are within this area, right? And also motor torque limitation. This torque must be, for example, 1 Newton meter, 2 Newton meter, something like that. So this is the result. When alpha 0, in that case, totally time optimal problem, right? Vibration, we don't care about vibration. Then this motion generated. You can see a video. Let's see. Right? The vibration, you see vibration here at the end of motion. But after applying this very small alpha here, consider trade-off, then vibration very much reduced. So video clear, becomes clear, right? In this case, video unclear by vibration. Motion time is a bit increased, but yeah, I think acceptable value. Motion time bit increased, but vibration largely reduced. And we conducted experiment when no vibration consideration, time optimal trajectory, this vibration, y direction occurred, right? After arriving the destination, yeah, this vibration remain. This is a time optimal trajectory from this position to this position. And after considering vibration by applying alpha 0.001, not 0, then motion changed like this. You can see the difference, red one. Then vibration largely reduced, right? Because this is just a bit faster than this one, but considering vibration stopping, yeah, later case much faster than this one. This still, we have to wait the vibration suppression at the destination, right? But here, vibration stops around here. So this is the, effectiveness of optimization, right? During motion, this vibration changed, and after arriving the destination, faster convergence achieved by optimization. And we consider all motions from here to here to here, from here to here. This is a bit old PC. Average computation time in optimization is around 7 minutes. Right? Some requires 50 minutes, some requires 3 minutes, or something like that. So there are examples. From this here to here, this smooth trajectory, from here to here, here to here, this rotation occurs, something like that. We successfully generated all optimal trajectories. And this is conducted around 10 years ago. But the company is still using this program for generating motion trajectories. Yeah, you imagine that if you generate this trajectory manually, considering motor torque, obstacle avoidance, vibration, I think it's no longer possible, right? The company is still using this optimization program we developed. Okay. And we conducted verified experiment, effectiveness by experiment, right, for all required transportation patterns. Okay, this is one example in industrial applications of optimization and dynamic control. Do you have any questions? If not,
Any question?
go. Yes, you have a question.
Yeah, I have question, Prof. Uchiyama.
Yes.
In the video you shared before, I would like to ask how do you select the alpha parameter?
Good question. So this is just a bit difficult to trial and error, actually, right? Because only slight change needed, right? So we can, for example, we cannot predict this difference. So, but yeah, basically trial and error. Yeah, only one parameter. If you have only one parameter to be adjusted, I think trial and error is possible. Right? If you have multiple parameters, trial and error is no longer possible. Yeah, that's a good question. So yeah, there's no reason basically.
Okay.
Normally we left one parameter for adjustment, final adjustment in applications. Yeah, controller design also, yeah, you have some gain remained to be tuned. Yeah, that's because simulation and experiment are normally different. So we have to have some kind of degree of freedom for tuning. So this is a kind of tuning parameter.
Okay.
Is it okay? Thank
Yeah,
you.
I mean, how sensitive the optimal trajectory if we put the different
Right.
alpha value?
Yeah, that's a good question. This is very sensitive. Yeah, I remember that. So normally first we apply one, so then motion becomes very slow. So we
Okay.
reduce it to 110, and again 110, and 110 something like 110 something, right? Very
Okay, thank
sensitive. Yeah, in this case, very sensitive. Yeah, it depends on the problem, I think. Oh, okay.
Okay, thank you.
Thank you. I think very good question. It's very good question. Yeah. One key idea is normally we have one tuning parameter remained for implementation. Any other questions? Thank you. Then I would like to go to next slide. Vibration, suppression, and energy saving. Yeah, still industrial problem, factory, in factory problem, right? This is around 10 years ago also. But recently, companies request going to outside motion, outdoor automation. Yeah, around 10 years ago, factory automation are a main topic for industry. But recently LiDAR camera more, reliable and less costly. So they are applying such kind of sensors and sensors to outdoor automation problems. Later, I'll explain this one. So next topic, this one. Machine tool and loader. So the topic is energy saving and vibration, again, vibration suppression of industrial machines operated by a simple motion trajectory. This is a key point. Simple motion trajectory is easily applied to industrial machines. They are published in American Control Conference, one of the, I think, major conference in control area, around 10 years ago. This is a loader we developed in collaboration with company. The name is battery loader. Normally loader has a cable and for charging the power, right? Some loader has, for example, 50-meter long. So cable will be damaged after, for example, 3 years, something. They have to replace cables. You imagine that they have to pull cables back and forth. The cable will be damaged easily. So they decided to change cable to battery. Actually, a battery requires long charging time. So we use capacitor for charging. Here's a capacitor. And when stopping, the capacitor is charged, right? And when moving, energy is released, used for motion. When stopping, there's some, electricity charging board somewhere, and when stopping, the capacitor charged. So we developed this system. I'd like to briefly explain about Japanese, Japanese industry, strongness of Japanese industry in this field. This is a production of cutting type machine tool by country, right? So, sorry, this is a bit old data because my work also a bit the old one. You can say around 25 years, right? More than 25 years, 25 years, less than 25 years. Japan is has highest market share. Even we are very small island country. I think this is a kind of our proud. Right? Here, I'm not sure you know Lehman shock. Lehman shock. This is very much depressed and recovered. The next one is Germany, right? Orange one. German cannot come back, right? Decreasing. But still, I think German is third place. And this growing one is Chinese machine tool, right? But most Chinese machines are used in China. Right? Ours and German products are widely used all over the world. Right? So anyway, you see, we sold many industrial machines all over the world. This is a fact. And also for industrial robotic market, considering this one, Japan also has a high market share. This is year 2015 data, sorry, 10 years ago. Global industrial robot sales, this one. And Japan occupies more than half, right? So 138,000 units. We sold this number all over the world. Recently, energy shortage and Earth environmental problem becoming severe, right? I think Indonesia also you have big heavy rain seasons compared to before. In Japan also, right? We are facing such big disasters, in particular heavy rain recently. So because we sold many products in the world, I think we are responsible for energy saving in this kind of robots or machines, right? Sorry, this is also a bit old data. World energy consumption by sector. Industrial occupies more than half, right? Next, transportation, residential, commercial. Transportation not so high, right? Some consider electric vehicle are needed, but industry has much higher than such kind of transportation field. And among industry, motors has highest energy consumption. I thought that heat might be the highest, but motors highest. Here the comment. Indeed, electric motors and the system they drive are largest single consumer of electric power. Approximately 50% total global energy consumption, right? And which generates big CO2, carbon oxide. So because we sold many machines all over the world, we are responsible for this kind of problems. Recent becoming a big problem. Right? This is my motivation of this work. As I explained, we sold many machines and they are operated around the clock all over the world, right? Night and day. So hence energy saving is required. Many machines are already currently used. They don't want to change hardware, right? That's costly. So I thought that control approach would be useful for implementation to these existing machines all over the world. And one more thing that in industry, feedback control is also difficult to be changed, right? Because feedback control system requires sensor. And if you, assign inappropriate gains, then system becomes unstable. Some industrial machines are not allowed to change controller gain. Right? Sometimes very dangerous. The system becomes unstable. So our target is simple motion trajectory design for energy saving. Because this company, use capacitor, so they asked us to reduce energy for motion. So this is motivation also. And most industry machines operated by, for example, Mitsubishi controller, industrial controller, or some other companies in Japan. So they want to use inexpensive controllers. And sometimes they allow us to use only this trajectory for motion, trapezoidal velocity profile. But this is velocity. So this includes acceleration, constant velocity, and deceleration, like vehicle motion in highway something, acceleration, constant, deceleration, stop, right? So we borrowed this industrial machine from the company, actually Mori-Seiki machinery. Right? You see this table motion here, right? So we assign acceleration T1 and assume T1 equal T3. So this is T1 0.1 case. This is T1 longer case, right? For example, this one blue trajectory, blue motion. This one, longer T1 motion. This area are the same because time times velocity will be distance. So these two cases, distance are the same, right? And motion time, total motion time are the same, right? So you cannot see the difference between them from video. But energy consumption very different between this red case, blue case. Yeah. Later I'll show you it. In this case, objective is minimize energy, right? Is our objective function, energy minimization. And we have 4 parameters here. 1, 2, 3, 4. One maximum velocity, acceleration, deceleration, constant time period. Right? And we assume this total motion time is assigned. You have to stop in 1 second something, right? So one constraint. And area is distance assigned. So second constraint. And third constraint, we assume T1 equal T3, right? Acceleration, deceleration must have the same time period. So in that case, among 4 parameters, degree of freedom, we have 3 constraints. So if we fix one parameter, then all parameters are automatically determined from the constraint. So in this case, variable is just acceleration time, right? This is short acceleration time and long acceleration time. You can take intermediate acceleration time. Then we'll have this kind of intermediate trapezoidal. So this has only one variable problem. So optimization easy. Right? You probably study this in high school to find the minimum point by taking derivative with respect to variable. Right? You can find local minima, something like that. Becomes very easy problem. And the constraints is we have to use trapezoidal velocity profile because inexpensive controller allows only this profile. Right? We can adjust only these parameters. And as I mentioned, motion time, total motion time, and distance assigned. Right? They are constraints. And yeah, I'd like to explain how to predict energy, consumed energy. Electric current depends on load, velocity, viscous friction, and inertia term. Like this is Newton's equation. Mass time acceleration and viscous friction and applied load will be applied torque or force, right? Force proportional to current. And voltage depends on current and velocity. This is called, if you are electrical engineer, you know, back EMF, right? Velocity increases, then friction increases. So voltage consumed. So depends on velocity and current. Yeah, this is Ohm's law, right? Probably you studied in junior high. Voltage proportional to R times proportional resistance, right? Ohm's law, and also back EMF term. And the power is current times voltage. And by integrating the power, we can predict energy, right? Voltage times I. And the voltage depends on velocity. And the current depends on velocity and acceleration. Right? Load is a constant. So by applying this current to here, we have velocity times velocity term here, and velocity times acceleration term here, right? And acceleration times acceleration. So, and from this trajectory, we know the acceleration, right? This inclination is acceleration. And also we know velocity. Yeah, of course we have constant term. So from this velocity, because we know this trapezoid, we assume this trapezoidal velocity profile, we can easily predict consumed energy. And by taking, so this profile depends on T1, as I mentioned. This is only independent variable. By taking time derivative, this one with respect to T1 and equal 0, then this provides the T1 that provides minimum energy. We can find local minima from our knowledge of we studied in high school. Now you can understand the image of this calculation. And we apply this idea to this industrial machines. Okay. Excuse me. And we changed T1 in experiment like this one. Here 0.05, 0.1 to 0.6. And distance unchanged. Time and distance unchanged. Only acceleration changed. Then this is consumed energy for 3 times trial. Almost consistent. And red one average of these 3 measurements. And this is theoretical optimal acceleration period, 0.16 something. And this is quite much with experimental results. Right? You can see reduction of energy from here to here. Also from here to here, around 30% reduction. Right? From here, 10% reduction is achieved. Right? So we can predict this 0.1 something, which provides minimum energy. Because this motion is continued 24 hours sometimes all over the world, right? This is small magnitude, just 10% of only for this machine. But yeah, if all countries apply this idea, just acceleration, then we can reduce, I think, the significant energy, right? For us environmental problem. We use this kind of analyzer for measurement, energy measurement. And the next one, we apply our idea to this industrial, this stable motion, right? This motion also the, widely used all over the world, simple motion. This is a theoretical profile, right? Acceleration versus consumed energy, right? And this cross 6 times, return motion experimentally, right? Average of 6 times return motion. So this is reliable. Not only one experiment. We continue 6 times repeated motion, repetitive motion. Then this experimental result, has a good coincidence with the good coincidence with theoretical result, blue one. And this company use this acceleration time, 0.05. They use maximum acceleration. So they consume this kind of energy, 3.6 joule, something. But applying our optimization, we achieve this 1.5 joule for the same motion, right? So more than 60% reduction is achieved. Actually, company is surprised with this result. Right? We wasted much energy for this kind of simple motion. Right? By just adjusting acceleration, you can reduce energy very much. I explained that. And next, not only for this kind of loader system, if you use rapid motion, this kind of vibration occurs. So company also asks us to reduce vibration by using only this trapezoidal velocity profile. Right. So in this case, of course, we have to minimize energy and variables. We change total motion time. In this case, we can change total motion time. So variable is this one and this one. Others are automatically determined. So new constraints is no residual vibration is requested. Here's a big residual. You can see big residual vibration, but they request no residual vibration. The key idea is to consider natural frequency of pendulum. Right? Probably you studied this one in high school also. Small length, small pendulum, short pendulum provides small natural period, right? And large pendulum requires longer period, like for motion. And we found this property analytically theoretically. If this T1 plus T2, second one is important. If T1 plus T2 is multiples of natural period, right? So for example, this moves one time with the time T1 plus T2, then residual vibration completely suppresses. If you are interested in it, you can check our paper in American Control Conference. So, and we verify this idea. So this is an unconsidered case. By applying this second property, I'm sorry. PowerPoint ちょっと stops. Moment. これでいけるかな。Sorry, moment. Moment, sorry. これ。これ消して。I should share. Slide. Can you see my slide?
Yeah, we can see your slide.
Okay. Sorry, ちょっとinconvenience. By applying this second property, you see vibration completely suppressed. For longer, this center of gravity is at the end, so this is longer pendulum case, and short pendulum case, this motion. Right. So only by using this trapezoidal velocity profile, by just adjusting T1 plus T2, we can achieve this complete residual vibration suppression. Because we can predict energy consumed, if you use this velocity, rapid motion, you consume this energy. You use rapid motion, consume this energy, right? If you want to reduce energy, you have to reduce velocity like this one. But vibration suppresses, can be suppressed. Okay, so this kind of the design can be possible by considering both energy saving and vibration. You can adjust velocity for reducing energy. There's a trade-off between velocity and energy. So the important point is that we consider only simple motion trajectory, which can be used in all over the world in industries. And only the adjustment of acceleration time is needed. So this is easily applicable to any field in industry. And we showed the validity by experiment. Okay, this is the second topic. Any questions? You have any questions?
Any question on the floor, please, students?
Okay. Seems not. Okay, so next, I'd like to go next.
Sorry, Prof. Uchiyama, since our
Yes.
student have a question about
Yes.
previous.
Thank you. Thank you. Very welcome.
Sir, I want to ask.
Yes.
Since many machines cannot change their hardware or feedback controls, what is the biggest challenge when applying energy-saving trajectories to other systems?
Yeah. Because you mean that challenge in our method or challenge in feedback control? Our method is, I think, easy to implement. Just change acceleration, right? For example, this one, just change T1, right? Then, sorry, I didn't share slide. Sorry, I didn't share slide. これでちょっと I cannot catch your question. In our method, very easy to implement. Just changing the acceleration. This, for example, this one, just changing T1. This is not so difficult. Then we can achieve big reduction of energy, right? But if you change feedback control, some companies, stability will be changed of the system, right? You studied control theory or control engineering. Stability should be analyzed if you change feedback gain or something. Yeah, for this is a local company in our area. There are no such engineer for tuning the controller. They just change motion profile, right? So, most cases, yeah, if you consider, for example, Fanuc or big companies or in Japan, Yasukawa, something, yeah, there are many control engineers, but local companies, they are kind of just users of this machine, right? This kind of loader something. They can change just trajectory profile. That's a challenge, right? Feedback control is a challenge for them. Is that the answer to your question?
Yes, sir. Thank you.
Thank you. Thank you for questions. Okay. So, can I continue?
Yes, you can continue. Thank you.
Yes. So I think I have 2 hours, right? Just next topic is, which one is interesting to you? So rotary crane problem, next one. Yeah. I think you can see my slide, right? Okay. This is published in this journal, right? So we, as I mentioned, we started the collaborative laboratory with Covelco construction machinery. In this laboratory, we can hire, for example, 3 researchers, PhD postdocs or something. So this is a relatively big project in Japan. So this is one target. They have this, they provide this kind of big crane, 100-meter height around. Actually, 80-meter height something, right? Then, you imagine that this, for example, boom must have light weight. So, this has this kind of truss structure, very lightweight. It means that not only load sway, but also tower torsion occurs. This is the problem. So operator must suppress not only load sway, but also tower torsion. This is tower torsion. Like kind of flexible arm. This looks like a flexible arm. So first we model dynamics, right, for control, for optimization. So this is a model of the such kind of big crane. This is a boom around 80 meter, right? And there are the 2 directional load sway, tangential. We operator rotate this boom by theta 4, right? Theta 5. And tower torsion occurs, theta 4. And because high dimensional dynamics is difficult to be dealt with, we apply just spring constant and viscous friction here. And this is a model of tower torsion, right? The same as the previous industrial manipulator problem, right? We consider just a spring constant K. In most cases in mechanical engineering, this idea is typical to consider vibration apply spring constant K and the viscous friction between this one, right? And in this case, we have two directional vibration, tangential and radial direction to the boom, right? And here this angle is fixed, assumed to be fixed, right? So this is a bit complicated dynamics because this is suffered from centrifugal force and Coriolis force. Coriolis are here. Inertial force, centrifugal, Coriolis, gravity, and tower tension. Highly nonlinear. And we check the validity of dynamics with experimental result. Right. This is applied motion. Black one is applied velocity. This one, velocity rate, velocity, actually velocity of theta 5. This motion, right? Then in simulation, this blue vibration occurs in tangential direction. Vibration of load. This vibration, right? And red one is experimental result. Even in this transient response, I think they quite much, right? And this is tower torsion. They also quite much, blue one, red one, simulation experiment quite much. So we consider this dynamics is sufficient to show to predict the performance. Okay. Then next we apply this optimization. And again, we apply this velocity, trapezoidal velocity profile. In this case, we use a kind of sine function here, acceleration, deceleration. Right? This is applied to this motion. And the motion time is, total motion time should be minimized, right? This one. And load sway, this one should be less than this value. Also, velocity should be less than value. They are constraints. And also, this tower torsion, theta 4 minus theta 5, should be less than this value. Okay, they are constraints. And also, this dynamics also constraints, right? They have to follow this dynamics. Motion must follow this dynamics. This is constraints. And this is objective function, right? Variables are this one, and this max, right? 4 variables. And also we, because experiment, we do experiment with this machine, but it's difficult to directly apply our idea to this one. Actually, we applied, but in the first stage, it's regarded as sometimes dangerous, right? If big vibration occurs, they said that this tower will be broken, right? Or this boom will be very much damaged. So, this is a bit serious experiment. So we established this machine in my laboratory, and there motion captures are installed to measure tower torsion. They are motion captures. And we apply this spring and damper here to imitate tower torsion. Right. This tower is twisted, right, from the motor by this spring. And we measure this twist by these motion captures. Okay. Then, also we compare this, laboratory sized crane is varied with the actual crane. So this is our this actual crane motion applying by this velocity profile. This is road sway. This is motion, and our experimental crane shows similar profile, right? Although this value is very different because actual crane very slow for safety. Ours a bit higher, right? 5 times higher, but the profiles are the same. You can see they looks similar. So we concluded that our machine experimental crane is valid, provides valid property. So this is the result. So as I mentioned, we design two trajectories. One is blue one without control. Sorry, they are in Japanese. Right? This is a motion of boom rotation. And by optimization, we obtain red one. And first we show blue one. So because of tower torsion, the load stops once here, even, finally there's big load sway remain. Even motion is must be very small, right? Motor motion very smooth, but tower stops because of vibration. And finally, big residual vibration occurs. Okay. This is radial, blue one radial load sway, and tangential load sway. Very big. They are measured by motion capture. And after applying optimization, motion becomes very smooth, right? No stopping during motion. And finally, almost no load sway. Very smooth. This is red one. Radial load sway, tangential load sway are very much reduced, suppressed. So this is the effectiveness of optimization, trajectory optimization. You see, we control only rotation, boom rotation, but we have to control both load sway. That's a bit difficult problem, right? Actually, by this boom rotation, radial load sway linearly uncontrollable. Right? This is controlled by centrifugal force, only centrifugal force, or Coriolis, right? So this is a bit difficult problem, right? There are two variables. Also theta phi itself, 3 variables to be controlled, right? 1, 2, 3 variables must be, and also tower torsion should be reduced only by this one motion, simple motion, right? If you are control engineer, you know the difficulty. You understand the difficulty. Only we can control only one variable, but we have to suppress this tower torsion, this load sway, and this is a radial direction, so linearly uncontrollable. Right? This is achieved by optimization. Okay. So this is we conducted similar experiment in previous years. We compared this idea and the proposed idea. Actually, this one doesn't consider tower torsion. So by considering tower torsion, we obtain much better performance. Like this solid line, right? Tower torsion reduced. if we don't consider Tower torsion, the big roadway or Tower torsion remained. So this is our original trajectory. And after considering Tower torsion, this motion is a bit prolonged, but roadway Tower torsion very much reduced satisfactorily. Okay, that's it. I'm here in plane control. Any question? Okay, no question. No question. Okay. Yeah, so I'd like to explain. Okay, can I continue?
Yes, you can continue, but actually I have one question about
Oh, yes,
previous.
yes. Please, thank
Uh,
you.
is there any limitation about how large the load sway in your experiment?
Limitation.
Yeah,
How
I mean,
large?
yeah, how large the load sway angle can be for the horizontal motion only.
Uh, yeah, I think theoretically, yeah, you can see my slide, right?
Yeah, I can see your slide.
Theoretically, yeah, I cannot say how large it is, but experimentally, yeah, we obtain this result, right? This is radian.
Mhm.
In actual crane, for example, this is used for construction site, right? They bring, for example, 2-ton load or 3-ton load, move up to the construction building, right? At the destination, they are accepting operators of load. So if load sway, for example, 1 meter load sway occurs, very dangerous for operators. You imagine that. Because it has 2-ton or 3-ton, like a vehicle, right? Vehicle moves 1 meter. And in the construction site, there's no space to escape in the building, constructing building. So operator will might get very much angry, right? That's very dangerous. Right? So this is 1 meter roadway is not allowed. So this is a limit. Of course, this is scaled, but this roadway is limit to be allowed for safety. So this is achieved by this control. Is that answer to your question? How big the load allowed or something? Your
Okay.
question is that. So this limit is, constrained by actual problem, actual on-site problem, right? 1 meter is scaled to this angle in this small experimental system. Is it okay?
Okay, thank you, Sensei. Okay.
Thank you. Thank you very much. So we consider real problem, right, for problem setting. So I think because time limited, this is the final topic today. This one. Next, excavate problem. I cannot go to mobile robot because time limited. I'm sorry about that. Excavate automation. This is also presented in this conference. Probably IES conference. This year held at Surabaya, Indonesia.
Yeah, we know that conference in Surabaya.
Really? We have a good collaboration with EPIS also. EPIS, you know, EPIS is kind of the National College of Technology. Don't you know EPIS? EPIS, no.
Is that Polytechnic?
Polytechnic, yes, Polytechnic.
Okay.
Surabaya.
Yeah, we know that Polytechnic.
Oh, yeah, okay. Yeah, this is held at that Polytechnic, Surabaya. Okay. Anyway, in recycle center, this kind of motion continued. Yeah, as I mentioned, the recent years, outdoor automation are highly requested in many companies. And yeah, compared to indoor, outdoor experiment, very hard for us. For example, in recycle center, operator moves this material, I mean, recycled material into belt conveyor for selection whole day. So also in seaport, non-packed materials, for example, coming from China, and this is must be transported to land, right? In a very short time at the seaport. And operator are very much rushed for this transportation of non-packed material to the land side. Because if you take longer time, you need to pay more money for parking the ship at the seaport. So this is highly requested. And also recently we are facing the population shortage. And we are becoming a very much elderly society. Skilled operator employment very difficult. Right. So automation is requested. So this is our target system. A truck brings this kind of material, and the excavator automatically takes it, moves it to belt conveyor, right? By detecting these kinds of cameras. Yeah, there are two cameras here, and this is our target. Then this can be automated. So we established this environment in the recycle center, right? We use RGBD camera, Intel Real Sense here, only one camera, right? You know, RGBD camera, not only image, but also distance to each point can be detected. D means depth, RGB depth camera. We use Intel Real Sense. Also, recently, GED is used for for the same purpose. Here's our student. And also we use OpenCV for visual inspection and Python for programming. They are free software. And first we have to detect this area by camera, right? It's needed for automation. This is the color image, right? And our student, German student, invented, there are many edges in this image, right? This area. So first we apply canny edge detection method. Then we roughly know here's materials, right? And also we apply so-called morphology transformation. First we shrink image to reduce noise, right? This noise and small one reduced, eliminated, disappear. Then again expand. That's a morphology transformation. Then we have this noise is reduced here, right? And we have, because this is expanded, we have this white area. And after having this one, we select maximum white area, connected area. Then we can extract material area, right? And next topic is optimize grasping position. First, I'll show the result of detection of edges, right? Even they apply shower for saving the dust. And also we can see sunlight. But under this environment, material area detection is, successful, like this one, in real time. Next step is to just select, preferable or, best area for transportation. The optimization of grasping position is next topic. And we divide this area into cells, and we assign a score to each area. For example, the height is important. Certain level of height is important for grasping. This area cannot be grasped, right? And also distance to excavator also criterion, right? And also flat area is better. Yes, it's not sure, but this inclination also of this area is can be a criterion. Okay, then by weighting them, we can select the best position for grasping. So this is an example of optimal positions. If you weight height more, this position is selected. And if you weight distance to excavator more, then this closest position selected. But it's impossible to grasp. And by considering the trade-off between distance and the height, this position are selected for optimal grasping position. This is looks appropriate position for grasping, right? This is an image of optimization. So this camera detects this area and we calculate optimal position. And this data is sent to PC in excavator. And excavator now knows which position is the best position. And in order to move this to here, we have to calculate inverse kinematics, which means that from this position, we have to calculate wrist angle, elbow angle, shoulder angle, and waist angle. They are calculated automatically by Python program. And also, next step is we know now joint angles. And we have to control the hydraulic system to that angle, right? So control a bit. This is not electric motor, hydraulic actuator. So we have to consider nonlinear controller for this. Okay. Then also this is written by Python program by our student. So this is a first experimental result. Right. Here's my student, and his hand is raised up. So this is a fully automatic. Here's a camera. You cannot see camera. Right. Overshoot. Here's a camera. Yeah, you see camera. Here. And the position detected and grasp automatically. And because this is first experiment, control is not good. Stop here, right? And overshoot and return to desired position and successfully moved to this container, right? So we successfully conducted this kind of first experiment. I'll show you this again. Camera. This is also overshoot here, but grasp it. If it moves, overshoot is big. This hits the wall, right? This is a bit dangerous experiment. So outdoor experiment is much more, in my view, much more difficult than indoor experiment. Also, yeah, this image is suffered from sunlight sometimes. And yeah, this day we have heavy wind. So motion suffered from heavy wind sometimes. Many disturbances. Okay, so this is another example of the optimization of outdoor industrial system. Right? Yeah, we have to consider many things for automation, not only recognition, visual recognition, but also grasping, position optimization, inverse kinematic calculation, hydraulic controller design. Right? Yeah, they're very challenging. But yeah, I think the automation of this kind of work can be useful for not only industries but also yeah our human activities, right? Because we Indonesia, I'm not sure, but Japan facing the elderly society. So this kind of automation is highly required in many fields. Okay, that's it. I think we have 10 minutes left. Okay, thank you for your kind attention.
Okay, thank you, Prof. Uchiyama. Anybody online or in the class, if you have any question about this topic, can
Question,
you?
Pak Deden.
Okay, thank you, Bu Rahmi.
Okay. Thank you, Prof. Uchiyama. My question is that have you also doing experiment with equipment using thermal, for example, thermal equipment?
Thermal equipment. Sorry, thermal. I cannot understand.
Yes,
That
such
word.
as boiler, maybe.
A boiler.
Or,
Sorry, I have no experience with such kind of. You mean thermal
yeah,
equipment?
thermal equipment.
But yeah, we have a professor because I'm in mechanical engineering. We have a professor regarding such topic. If you are interested in it, I can introduce a professor to you.
Yes. Yeah,
But
because
not control field. He's just yeah, thermal kind of scientific research.
yes, because in Indonesia currently energy also important issue,
Mhm.
and most of industry they use like thermal equipment like boiler or pump or
Yeah.
compressed air in, and this equipment they consume energy significantly in industry.
Yeah, right. Yeah. I'm collaborating with the Malaysian professor, palm oil plantation automation. Yeah. Yeah, I understand the importance and the difficulty also, right? That's also outdoor equipment. So, experiment itself is very challenging, right? No, yeah, I understand.
Thank you.
Thank you.
Thank you,
Thank you very much.
Professor Uchiyama.
So your university title is multimedia university, but yeah, you have such kind of variety of topics, including mechanical engineering, right?
Yeah, we have
That's a compressor or yeah, such kind of boiler, topic in mechanic, not multimedia, right? That's interesting to me.
Yeah, we have three engineering department, Sensei. We have computer engineering, electrical engineering, and from us is from engineering physics, which focus in energy management and also in instrumentation. So we also learn about control engineering in this case.
Oh, okay. I understand the structure of your university. Right. Thank you.
Okay. Student, any question? or on the online? Any question? Maybe I have one question about the last excavator for grasping position, Sensei. Is there any consideration about the lighting effect for the accuracy of hip detection? We know that lighting is also have a bright light, glare, or maybe shadow. Do you have any consideration to make it the detection is accurate?
Yeah, that's yeah, also good question. You mean this RDVD camera, right?
Yep. Mm.
Yeah, yeah. Actually, we conducted this. Can you see video? Right. You can see video of detection.
Yeah.
No. Right. This is a result of detection. So, yeah, for practical implementation, I think this is sufficient, right? Yeah, even by this is a shower for saving dust. This is still, working. But yeah, as I mentioned, I didn't check the such kind of relation between the precision and the lighting condition, lighting effect, something. That's yeah, yeah, good direction, I think, for the next step. Yeah, my idea is to use yeah, because sunlight comes from this direction. My idea is to use multiple cameras, like this kind of multiple cameras. Then even sunlight comes this direction, this can detect the object, right? When sunrise. And when sunset, we use this camera. Yeah, such kind of, because camera itself is not so expensive. Yeah, around $500 something. So we can use multiple camera for improving the precision.
Okay, thank you for your attention. And again, thank you, Prof. Uchiyama, for participating in our guest lecture. Thank you for attention, and we look forward to welcome you again in our future academic events. Have a wonderful day, and thank you very much. Have a nice day, everyone. Thank you.
Thank you very much for your attention and yeah, this opportunity. I really appreciate it. Thank you.
Thank you. Bye
Thank
bye.
you, Uchiyama Sensei. Thank you very much.
Thank you very much. Bye.
Bye.